Today we are going to continue our discussions on the quantizers for speech signal, and especially we will deal with the mu law and optimum quantizers. Okay. Now, we have described in the last class the logarithmic encoder and the decoder, and there you must have noted that in the case of logarithmic encoder and decoder, the signal to noise ratio is not dependent upon the variance of the signal, and it is only dependent upon 1 upon sigma epsilon square, which means to say that only the step size is the deciding factor. So this really makes it a very good candidate for designing the quantizers for the speech signals, and we are going to consider this. In fact, one of the difficulties which one faces with the logarithmic encoder decoder combination is that the logarithmic encoder decoder essentially has got a very large dynamic range, okay, and in fact the dynamic range here happens to be infinite, and that is why we have to design with very large number of step sizes, okay, if we have to make it practical. So it is not actually practical, so we have to really modify the scheme. And also another aspect which we have noted in the last class is that we are providing some approximation to the logarithmic function. In fact, you have seen that the exponential approximation we are doing, and only that is leading to the derivation that the signal to noise ratio was independent of sigma x square, right? So now we are going to have another logarithmic encoder decoder, but where the transfer characteristics is slightly altered. In fact, what we have is some kind of a block diagram like this, where the input will be the xn, and then we will be having a transformation function which we call as f, which will be a logarithmic function basically, and then this will be followed by the quantizer which we are calling as the q function, and then we are following it up with the encoder, and the encoded output will give us C of n, and there will be the step size. So the step size, which is the delta, that will be controlling both the quantizer as well as the encoder. And in fact, the corresponding decoder will be that the input will be the Cn, and this will be followed by the decoder, and then we are going to have the inverse transformation. So whatever f we are using, we have to use f inverse of this, and that will generate the x cap of n, which is going to be our reconstructed signal. So x of n is the original input, and x cap of n is going to be the reconstructed output at the decoder end. So now we have to see that what is the f function that one can use instead of using the direct logarithm. Earlier we were saying that we will be using log of the modulus of the xn, okay, and we will be also deriving the sine of the xn, but instead now we are going to consider a function which will take care of the deficiencies like utilizing the dynamic range as well as the approximation to the logarithmic characteristic. So the transfer function, or rather this transformation f, that's what we design, is like this, that we say y of n. In fact, y of n will be nothing but the output of this f. So here we have the y of n available as the output of this transformation block, and we are going to write y of n as f of xn, and this is given by the x max, okay, which is going to be the maximum amplitude of the signal, maximum possible amplitude, and this multiplied by log of 1 plus mu into mod of xn divided by x max, and this upon log of 1 plus mu, and this to be multiplied by the sine of xn, where sine of xn we already said that will be equal to plus 1 if xn happens to be positive and minus 1 if xn happens to be negative. So this is the expression, and this is actually called as the mu law. So this is, as per the mu law characteristic, the transformation f would be like this. Now you can examine this equation, okay, yn is equal to x max multiplied by this expression. Let's call that as equation 1, and you can see that if we substitute in this equation mu is equal to 0, okay, but a direct substitution of mu is equal to 0 would mean that we get a 0 by 0 form. So if we mathematically manipulate that, okay, by taking the derivative of the numerator and the denominator, and then what we derive is simply this, that you can derive that for mu is equal to 0, we are going to have yn to be equal to mod of xn into sine of xn, okay. This x max term gets cancelled ultimately, okay. Here there is one x max term over here, and here there is another x max term. This x max term will ultimately come to the denominator if you see. So that ultimately you will be left with mod of xn multiplied by sine of xn, which is nothing but xn. So yn is equal to xn. So at mu is equal to 0, okay, the characteristic that we will be obtaining if we happen to plot yn versus xn, then the characteristic will be a completely linear characteristic that would pass through the origin. So it would be exactly like this, in fact with a 45-degree slope. So if you are taking xn values, if you are plotting in this direction, and yn values you are plotting in this direction, then xn is going to be equal, then yn is going to be equal to xn. So this is the curve that you will be having for mu is equal to 0. So somewhere at this point, let's say that we have the maximum possible value of xn, that is x max, okay. So when xn is equal to x max, likewise the yn also will be equal to x max according to this. Now if we go by this equation and then try to plot the yn versus xn curve for different values of mu, we will be obtaining it like this. In fact, this was for the case of mu is equal to 0, and then we can go to another extreme, that is for very large mu, okay. For large mu, large values of mu if we plot this equation, okay, and also if we take the larger value of xn, means xn which is more closer to x max as compared to xn closer to x0. So, when we take large mu and large xn, then so large mu and large xn would give rise to an approximation in the value of yn, and we can write that mod of yn is approximately equal to x max into log mod xn upon x max. Okay. So, this is for large mu, and in fact if we directly go by the plot corresponding to this equation, that is equation number 1, we will be obtaining the characteristics something like this, that for increased value of mu, okay, what do we expect? Should the curve be like this or should it be like this? What do you feel? I mean, should it go like this or should it go like this? Because this will approximate the logarithmic characteristics more, so this will be upward. So, we will be having a characteristic like this for, let us say, if we take mu is equal to 5, we may find a characteristic which will lie above this mu is equal to 0 characteristic. So, mu is equal to 0 is actually the case of no compression. You see that there is no signal compression that is happening, because whatever is the value of xn, yn is having the same value. Whereas, here you can see that for these values of xn, you will be finding that the incremental change in yn is much smaller. Okay. And if we increase the value of mu further, then we will be observing the characteristic like this. So, we may observe, let us say for mu is equal to 50, we may observe a curve like this. For mu is equal to 255, we may be having a curve like this. So, this will be for the large values of mu's, we will be having like this. So, this is a typical characteristic that we will be obtaining, okay, for, so this is x max. So, we will be obtaining for yn versus xn for different values of mu. Okay. So, now in terms of the characteristics, I mean one can observe that if we are plotting the value of x cap in versus xn. So, x cap in means that at this point, okay, when we quantize it, so this was yn, so yn is after the transformation, and after the quantization, this we are calling as the x cap of n, right. So, this x cap of n, if we plot against xn, then the characteristic will be something like this, that we will be having, if we plot xn in this direction and plot x cap n in this direction, then we will be observing a nature very similar to what we had just shown for yn versus xn, because it is ultimately the yn which will be quantized, not the xn directly. And for different values of xn, rather to say corresponding to the decision levels. So, if we mark the decision levels corresponding to xn, then we will be observing, suppose this is x1, this is say x2, this is say x3, and this is say the value of the ultimate x max. Okay. And we will be observing that the value of x cap would be something like this, that here we will be observing the x1 cap, okay. So x1 cap would go like this, and then we will be observing this to be the x2 cap, okay. This will be the x3 cap, then we will be finally having some, I mean there may be some more intermediate levels like this, but if it is just having, let us say, 1, 2, 3, 4 levels on this side, okay, and in fact this will not be 4 level, this will be 8 level. Why 8 levels? Because the signal is a bipolar signal, okay. So x of n can have samples which are positive, can have samples which are negative. So the actual range will be minus x max to plus x max, okay. So since we are having 4 levels in this example, since we are having 4 levels corresponding to the positive signal, we will be correspondingly having 4 levels for the negative signals as well. So and this characteristic will be antisymmetric about the origin. So if we just make an antisymmetric version of this curve and then we plot xn over its range from minus x max to x max and just extend the characteristic on the negative direction with an antisymmetry, then what results is 8 different quantization levels. That is what we will be obtaining. So now with a characteristic like this, okay, I mean when we have x cap n versus xn being plotted this way, now we can derive the expression for the signal to noise ratio in a manner very similar to what we did earlier for the uniform quantizers. For uniform quantizers, as you remember, that we had obtained the signal to noise ratio, which I am just reproducing for your reference, that the signal to noise ratio was computed like this, that the for uniform quantizer we had obtained the SNR in dB was equal to 6B plus 4.77, okay, minus 20 log to the base 10 of x max divided by sigma x, okay. And for mu law quantization, okay, what we are describing here, if we are following the similar derivation approach, then one observes the SNR dB to be like this. SNR expressed as dB is equal to 6B plus 4.77. So up to this the terms are equal, but not beyond this. After this there will be a term that is 20 log to the base 10 1 plus mu minus 10 log to the base 10, and this will be 1 plus x max upon mu sigma x, this term square plus root 2 into x max upon mu sigma x, okay. So this is going to be the total expression. So you can see, you can just compare these two equations, and here you will be finding that here there is a direct term 20 log of x max by sigma x. In fact, this is the term which we criticized, because we had said that if sigma x happens to be small, okay, if the ratio of sigma x by x max, okay, that happens to be small, in that case we are going to have a reduction in the signal to noise ratio. Okay. Now, in this case also there is a reduction. Firstly, that there are two terms which are contributing to the reduction. One is this minus 20 log of 1 plus mu, but for a particular design of the quantizer, mu is fixed, right. So, this is a constant quantity which will be subtracted. So, we are not bothered about that, but we are more bothered about the term that is signal dependent. Okay. So, there is a sigma x term. Okay. So, you can see that x max by mu sigma x square, but if this is a small quantity, in this case there is a square term which is coming over here. So, this is furthermore reduced, and you can see that this term is much less sensitive to this variation in x max by mu sigma x. In fact, mu also happens to be a larger quantity. So, if you are finding, so as a result of this, the term that is going inside this logarithmic argument, that term is not very sensitive. So, as a result of that, if we happen to plot the signal to noise ratio from this equation, if we plot signal to noise ratio against the quantity x max by sigma x, in that case we will be finding more or less a constant, I mean much less variation will be found, whereas in this case we will be observing a fall, although it is a logarithmic fall. So, now better to plot the two situations, that is to say uniform quantizer and mu law quantization, we can plot on a semi-log scale. If we plot, where this x max by sigma x will be plotted on the horizontal axis, which will be on the logarithmic scale, and then the SNR in dB, if we change it. So, here if we happen to just take the if we happen to plot this, then we will be observing a characteristic that is very similar to this. So, we will be having 10, let us say that here we have 100 and here we have 1000, right, because we are going to plot it in the logarithmic scale. So, x max by sigma x, we plot it like this, and then the SNR is plotted this way. So, then we will be having for b is equal to 5, let us say. See, here you see that it is dependent still upon the b, that is the number of bits. So, here it is 22, and we can see that it is like this. Then, so this is for b is equal to 5, and then we will be observing that b is equal to 6 would be something like this. This is for b is equal to 6, and for b is equal to 7, this starts from 34 dB onwards, and then we are observing it like this. So, this is for mu is equal to 100, all right, and we can see that here the variation is something of this nature, that for b is equal to 5, okay, then for b is equal to 6. So this is for the case of the uniform quantization. So this will be the characteristic for b is equal to 7, right? And this solid lines are all for the mu law, right? And for the uniform quantization, see again, because we are plotting in the logarithmic scale, and this is also in the so this is in the logarithmic scale, and the expression of SNR also is logarithmically changing. So we can expect a straight line for the uniform quantization. So you can see that b is equal to 5 characteristic would be like this, and b is equal to 6 characteristic may be like this. B is equal to 7 characteristic could be like this, and b is equal to 11 characteristic could be like this. So all these dotted lines are for uniform quantization. Okay. So now you can see that what is the conclusion that we can draw out of it? That for lower value of x max by sigma x, lower value of x max by sigma x means that where the value of sigma x is closer to x max, okay, means for very large signal variance, okay, we can see that the uniform quantizer is having a much more value of the signal to noise ratio. It's having a much better signal to noise ratio. Just look at this point, okay. Here for b is equal to 5, and for a very low value of maybe this is 2 or 3 will be the value of x max by sigma x over here. You can see that the b is equal to 5 curve happens to be at a much higher level as compared to the b is equal to 5 curve for the mu law. So definitely it leads to the conclusion that as if to say this is better. But again you see that for the variation of sigma x, okay, once it crosses this point, okay, maybe that this is with x max by sigma x at a value of 7, and beyond that we are finding that this uniform quantization curve falls rapidly. So in this case for b is equal to 5, the mu law characteristics is giving a much better SNR, okay. It is more or less constant. It is only beyond certain stage that we are finding that for further larger value of x max by sigma x, okay, we are going to have a fall off. In fact, this is quite expected also from this equation. You can see, look at this equation, that if this term and this if x max by mu sigma x that happens to be sufficiently large, only then there will be some fall in the characteristics. So this is what is happening for the mu law quantized version. But very interestingly, you can see that for a reasonably higher value of x max by sigma x, which is typically expected, you can see that the value of the so you can see that the value is equal, the SNR is equal at this stage. That is to say that near about 100 we are finding that the SNR is almost the same, okay. So you can see that whatever value we are expecting with only 7 bits, for mu law with only 7 bits we are having the SNR to be equal to that of b is equal to 11, right. So this suggests that the characteristic will be much, I mean this really suggests that for the case of mu law, we can go in for much lesser number of bits as compared to what we will be doing for the uniform quantization, right. And then we can have a very similar plot for a higher value of mu. Okay, let's say that we plot the same thing for mu is equal to 500, and in that case, what are we going to obtain? So this is for mu is equal to 500. Now tell me that, again look at this equation and tell me that if the value of mu is higher, okay, instead of 100 if we make it 500, what would you expect out of the SNR value? SNR will drop down, okay. And in fact, it is seen that going by this equation, the SNR will drop down. In this case, I mean from 100 to 500, if we use the actual values, we will be finding that the SNR drops down by nearly 2.5 to 3 dB. Okay. So here we will be observing that it will be at 19.5 and then it drops down much later. So this is for B is equal to 5, and for B is equal to 6 it would be like this, okay. For B is equal to 7 it would be like this, okay. The values instead of 22 has come down to 19.5, here this has come down to 25.5 dB, and here it has come down to 31.5 dB. A uniform drop of 2.5 dB has happened. And then again we will be observing, I mean I am not showing the other things, but again for B is equal to 11 we can see that the characteristic makes an intersection at this particular point, okay, which means to say that beyond this value of x max by sigma x, okay, we are going to find that this mu law is going to give us a better characteristic. In fact, no, it won't intersect at two places. It will be something like this, not exactly what I have shown. So beyond this value of x max by sigma x, we will be finding that the mu law is going to perform better. Whereas for smaller values of x max by sigma x, the uniform quantizer is going to perform better. But this means to say that although we may be having a better signal to noise ratio for the uniform quantizer case, and the signal to noise ratio in this case suffers somewhat, but this nature of the characteristic that it is totally uniform with respect to this, okay, this helps a lot. Now so now we can go in for the case of the optimum quantizer. You see that this mu law quantizer, this achieves a constant SNR, okay, over a wide range of signal variance. Now there is some sacrifice in the signal to noise ratio performance, but instead if we consider the design of optimal quantizers, okay, in the case of optimal quantizers, what we should do is that the quantization levels should match the signal variance. And how do we do that? So First thing is that the variance of the quantization noise, that we can write like this. It is given by sigma square E is equal to the expectation of E square n, and this is equal to E of x cap n minus xn whole square. Okay, and this let us call as the equation number 2. Okay, and in this case x cap n is equal to the quantized version, that is q of xn for an optimal quantizer. That means to say that xn will be directly followed by the quantizer. We are not using any other transformation. So it is just xn followed by the quantizer. So x cap n, that is the quantized value, is the q of xn, and in general we will be having m quantization levels. So if we use m quantization levels, in that case we are going to have minus x cap minus m by 2, x cap of minus, no, not minus, sorry, x cap of minus m by 2, x cap minus m by 2 plus 1, so on, x cap minus 1, then x cap 1 up to x cap m by 2. These are the set of m different quantization levels, right? Now, what we do is that, so in this case m will be considered to be an even number. Okay, and the quantization level that is associated, so the quantization level associated with the xj minus 1 to xj, this is denoted by x cap j. Now, when we have a zero mean amplitude distribution, in that case we can define that x0 will be equal to 0, and then furthermore if we assume that the density function is non-zero for very large values of x. Now, where we can have such kind of situations? When we have the Laplacian PDF or a Gaussian PDF, in that case it is going to have a zero value only at infinity. Okay. So, going by that, so if the density function is non-zero for large amplitude, then we can also assume that x plus or minus m by 2, that means to say that this level and this level we are setting as the plus minus infinity. Okay. Now, with this assumption we can write down the variance. The variance is expectation of x cap n minus xn square, and xn square is nothing but this x cap n minus xn whole square is nothing but e square of n. And when we have these two, that is to say the zero mean amplitude distribution, and then for large signals we are having for large amplitudes we are going to have the non-zero values. In that case we can write down the sigma square E as this. That means to say the expectation can be written as sigma square E is equal to the integral of E square times the probability density function of the error PEE DE, right. So, this directly follows from here when we incorporate this assumption. Now, if we plot the error quantity, that is to say E, when we plot against the X, okay, in that case we are going to have some kind of situation like this, that supposing this is X0, okay, and if this is say X1, if this is X2, like that, okay, and in this case we have X of -1 and here we have X of -2, all these different decision levels, then I mean corresponding to these decision levels we are going to have the value of the quantizer so making a discontinuity, okay. The error term will lead to a discontinuity corresponding to the case when X is equal to X0 or X is equal to X1 or X is equal to X2 at those points, okay. And again midway between this X0 and X1, what is going to be the value of the error? That is also going to be 0 at the midpoints. That means to say that if we say that X0 plus X1 by 2 or X1 plus X2 by 2, at these points the value of the error is going to be 0. But when X0 is making but when the signal just reaches the X0, in that case it is making a transition from the negative error to the positive error. Again at this point it is becoming 0, means that from the positive error it drops, okay. And beyond this, if we increase the value of X further, in that case we are going to have a negative error, and then at the value of X1 it is again going to make a transition. And if it is a uniform quantizer, then all these levels would have been as same, okay. But in the case of non-uniform quantization, we are going to have a value, I mean we are going to have a characteristic which may be like this, okay. Again just extending the same thing on the negative side, we are going to see some kind of error characteristic which would be like this. Sorry, it should be more like the midway, and then here it will be X of -2. So the error versus X characteristic would be something like this. So this is the quantization error versus X, right. And now we can write down the error, okay. The error is nothing but X cap minus X, and then we can say that by making a so here with E is equal to X cap minus X, we can write down that the probability of error, the probability density function of error PE of E, we can write down as PE of X cap minus X, and this by change of variable we can write down as P of X by X cap into X by X cap, and this could be defined as Px by Px of X. So as a result of this, we can write down the sigma square E as the summation I is equal to minus m by 2 plus 1 to m by 2 integral x of minus 1 to xi into xi cap minus x whole square into px dx. Okay. This is by direct substitution of this equation, right? So this was the earlier integral equation. What you had seen was in terms of the PEE. So it was E square PEE dE, and instead by change of variable we have made it, the E square remain as it is, but it is changed to PX dx. Okay. Now what we have to do is that this variance term, this error variance term, okay, this noise variance term, this has to be minimized. With respect to what? Now we have to design the quantizer. So designing the quantizer means what are the decisions that we have to make? We have to make the decision about x1 to x m by 2. So all the decision levels has to be decided, and then all the reconstruction levels also are to be decided. So all these happen to be the variables, and what we have to do is to differentiate this error term with respect to the quantities, with respect to the individual quantities like this xi's, and if we differentiate that and we equate them to 0, in that case we are going to have a set of equations. Okay. So by differentiating sigma square E, with respect to each parameter, we can get this set of equations: integral xi minus 1 to xi of x cap minus x whole square px dx, that is equal to 0 for I is equal to 1 to up to m by 2, and then we are going to have xi to be equal to half of xi cap plus xi cap I plus 1 for I is equal to 1 to m by 2 minus 1. Okay. And by our assumption we are having x0 is equal to 0 and x plus or minus m by 2 is equal to plus minus infinity. Now if we solve these equations, okay, in that case we are going to find out the value of this decision levels and the reconstruction levels, and that gives us an optimum quantizer. Now the point that we have to discuss is that, is optimum quantizer the best solution for speech coding? Unfortunately not, because although the optimal quantizer is going to yield a better signal to noise ratio because it is matched with the signal variance, it is going to give a better signal to noise ratio, but it performs poorly, especially in the case when in between the speech waveforms we have got silence. Okay. So for the speech signals the optimal quantizer may be okay, but whenever we are having the silence in between, in the case of silence what is happening is that the signal amplitude is already too small, and when the signal amplitude is too small, in that case it makes a to and fro jump between the minimum quantization levels. Okay, so it will make a jump between x1 cap and x1 cap, it will make a jump between x cap 1 and x cap minus 1. Okay, and if the step size of this happens to be large, in that case it is going to produce much larger error. Okay, And whereas in the case of the mu law compressor, okay, one can design the step size of the minimum signal to be much smaller as compared to the step size for the larger signal. So as a result of that, for the silence duration, okay, the change in the quantized levels will be much less for the mu law as compared to what we will be getting for the optimum quantizer. So although it is called optimum quantizer, for the speech signal, just let us remember that mu law is going to serve as the best performance, is going to serve with the best performance, because it is also taking care of the non-speech condition. That's to say, when the silent case is considered, it is going to be much better, right? So with this, now we can go in for the discussions on the next version of the quantizer, which will be actually the adaptive quantizer. Because you see that ideally what we should do is that we should design a quantizer that suits, or that adaptively suits to the signal level, that as the signal level changes, okay, as the signal variance change, okay, we should have the change of the deltas, okay, adapted accordingly. Okay, the step sizes must be adapted accordingly, and that is what we will be studying about the adaptive quantization case, okay, in the next class. Thank you.